So we haven't talked much about memory diagrams. So as promised, today and Friday, all about memory diagrams. I have a few slides. They're on the lecture slides for today. I won't get to them today if the last lecture is any indication. I have two memory examples, and I only got through one of them. There's a lot of moving parts with these things. I only got through one of them in the last lecture, so that's what I expect. But if you want to look at those slides, I don't know if I'll have a time to get to them. Maybe Friday, maybe the following week, maybe never. But it's about interpolation and compilation. It's stuff that you won't be quizzed on, but it's nice to know kind of stuff. So if it does get cut, you know. Paul did cover that content in the earlier lectures, so if you do want that, check out his lectures or check out the slides. So what I want to do is an example. You have the quiz next week. We got to get you ready for these memory diagrams, and I've only done one so far. We got to get caught up on that. If you've had lab this week, you've seen 3 examples. If you haven't had lab this week yet, you're going to see 3 examples in lab, which is basically going over a sample quiz. It's the ones posted on the course website for the lab. I'm going to go over an example today. We're going to start with the code so we all know what this method is doing, and then I'll jump to the memory diagram, and we'll explain how this thing works. We're going to trace through all of what happens in memory. So this can be found in the examples repo, live coding LO1 change array. Before lecture, I did about an hour ago or so, posted the code that I'm going to use for the memory diagram. When I live code this, it'll look a little different. I'll do things a little bit different, just however I decide in the moment. But if you want it exactly how I'm going to do the memory diagram, I guess not exactly because I changed one thing that I scribbled out here. That's in the repo. Pull the repo to get the latest code. This blue arrow, click that, and it's going to update this file with all that code that I uploaded an hour ago. Okay, so what we want to do is write a method that's going to take in an array as a parameter, or as we'll see in a bit, a reference to an array, multiply all the values of that array by 2, and then return the sum of the values of the array after they're multiplied by 2. So we're going to call this, and since I want to get to the memory diagrams, the main method I'll write. I'm not going to do formal testing and stuff. I would love to, but there's just not time. So I'm going to create an array with the values 2, 5, negative 3, call times 2. After this is called, this array should have the values 4, 10, negative 6, and result should be the sum of those values, which should be 8, and then print 8 to the screen. So that's what we expect to happen when this is called. So let's write this thing. Def times 2 is going to take an array of ints, return an int, and we're going to iterate over the values of this array, multiply them by 2, and get whatever we need to do done. So we'll be tempted to iterate over this thing. We saw in Scala how to iterate over the data of a data structure. So I would look at the values in input, then do something with these values, multiply them by 2. I don't know, values times equal 2. I don't know. That ain't going to work. Oh, actually, it did give me an error. That's not working. What we really want to do is do input of some index equals input of that index times 2. Really what we want to do is get the value at an index, multiply it by 2, and then set the value of that index by the result of that multiplication. This is what we want to do. So similar in 115 when this situation came up, we don't want to iterate over the values of this array. That's not going to do it for us. That's not quite going to cut it. We don't want the values 2, 5, negative 3. What we want to do is iterate over the indices. If I could spell, it'd be better. Did I just spell it wrong? What happened there? I want to iterate over the indices. So for each index, and the indices of that array do something. Now I'm iterating over 0, 1, 2, the indices of this array. This array has size 3, so I'm going to iterate over those values, 0, 1, 2. Now I can access the value at each index, multiply it by 2, and set it equal, overwrite what was in that array. Yeah?
Unit. There's an issue.
Yes, because I'm not done writing the method yet, so there will be errors here. So what's this error mean?
That you're returning a unit.
Yes. So I said I'm going to return an int, but I never wrote my return value yet, so I'm getting this error. Expected int, found unit. Unit is shorthand for nothing, or longhand. I guess it's shorter. So I'm not returning anything. I have to return an int because I promised I would return an int.
For the short term unit.
So let's set that up. This method should return the values, the sum of the values after multiplying by 2. So let me get an accumulator set up. Hell, let's even call it ACK for accumulator equals 0. ACK plus equals input of index. Being careful to make sure I get that after it's multiplied by 2. Get the sum of all those values after multiplying by 2. ACK. Done. I don't want to spend too much time on the code. I think this one's fairly straightforward. There's a lot of new syntax that I'm sure you're still getting comfortable with. How to access and modify arrays, iterating over arrays with indices, return values. But aside from that, the logic here, not too much going on, because I want to use this as a memory diagram example. So I don't want the memory diagram and the code being overwhelming at the same time. It should only be the memory diagram that makes you want to cry today. So let's run this, make sure it prints out 8. All right. Feeling good? Let's switch to this. I'm still figuring out, I haven't used this document camera in years. So I'm still getting used to using this again. I might find an electronic solution to do these, but for now I'm going to stick with the document viewer. But as these examples get larger, it's getting hard to fit everything on here. So bear with me as I'm getting used to this again. I had to make a quick change. This was causing problems in the last lecture. So you get the latest and greatest version of this code of storing that in a variable named RAM, which I need to declare. And then setting the parameter equal to that. So let's go through the memory diagram that. And please ask questions to this if anything doesn't make sense. By next week's quiz, you have to be at the level where you could look at this program and draw the entire memory diagram. So any questions? I know this is only the second one I've gone over, and I'm doing new stuff in this one. So please ask questions. You got today, you get your lab. Please ask questions in lab. You got 2 hours with the TAs explaining this stuff to you. Make sure you're ready. Get into next week. Go into that quiz hot. Kill that quiz. Get it done. So you don't even need that second opportunity. Get your application objective too while you're there. Get all that stuff. That's where we want you to get at. Ask questions until you're comfortable you can do that. I got the chat open. I don't believe we have any TAs in here right now. I didn't see them. But I got the chat open, and raising your hand always works. Let's do this. Google, stop listening. Okay, so to start the memory diagram, we're going to start with 3 columns, or I guess start with 2 columns. You also have the advantage of I know how to allocate my space a little better after just doing this in the last lecture. We have the heap, which I didn't talk about last time, which we will talk about today. And then we have the stack, the memory stack. And this is everything that's represented in your memory. When your program's running, when we draw these memory diagrams, this is literally everything that's on. Not literally, I have to hold that back. I hedge my bets a little bit there. This is what's happening in your RAM sticks. On that silicone, This is what's happening on those sticks when your program is run. This is what's stored in memory while your program is running. And this is where we're focusing on how your programs run, not just that they run. This is how your programs are run in the machine. That's what we want to see. How are these programs ran in your machine? Not just, oh, it gets the right answer, good. How did it get that answer? That's what we're getting at with the quizzes. Can you show me what's happening in your laptop when you hit that green go button? So that's what we want to get at. The stack and heap are two different types of memory. The stack is separated into name and value. And this is whenever we have a variable or a value. I'll use variable interchangeably. When I say variable, I'll use that to mean either a val or a var. Just to keep things simple, I'm already trying to say method and function at the right time. In LO3, I'll start saying function. Argument and parameter, there's enough to keep track of. I'm just going to call them all variables for the sake of memory diagrams. So the variables are going to go with their name and value on the stack, whatever's stored in that variable. And this will include, well, every variable, but anything that we call a primitive, which will map to a Java primitive. If you don't know what Java primitives are, that's 100% okay. I don't expect you to. But we'll borrow that term primitive, which includes ints, doubles, longs, floats, booleans, and a little bit, arguably, strings. We're going to treat strings as primitives. If that bothers you, well, we can have a long discussion about that. And did I get them all? Boolean, did I say Boolean? These types are going to go on the stack directly as values. So when we have an int on the stack, the name of the int and then the value of that int directly. Everything else goes on the heap. Everything else goes on the heap. For our purposes, for what we know, our knowledge of Scala right now, this is lists, arrays, and maps. And for now, we're just going to see arrays. And I promise you, arrays are going to be the only thing on the heap on the quiz next week. So I'm going to show you arrays today. Linked lists and maps, and linked lists especially, get a lot more complicated. Linked lists is a big LO4 topic, so we'll wait till LO4 to really dive into it. But everything else is going on the heap. For our purposes, that's arrays right now. That'll go on the heap, and the value on the stack is only going to be a memory address or a reference to that array. So when we get to our very first line, we have a variable named argument. That's assigned a reference to an array. Whenever we have this, we're going to draw the array on the heap as a rectangle with boxes for each of the values. An array can't change size. So when I create this array, it will always have 3 elements. So I create an array of size 3 by drawing a box with 3 boxes. That's my array. And that's going to go in the heap with values 2, 5, -3. And the way heap space works is it's very unstructured. It's very chaotic. Things in the heap can be anywhere. This is just a big pool of memory that we get to use. The stack is very structured. This is a last in, first out data structure. Things have to go in order in the stack, and the order is very meaningful in the stack. It's very structured, very orderly over here. The heap is a mess. So when we put something on the heap, whenever something's on the heap, we have to know where it is because there's no organized way of finding it. So the way to find that is by reference. We'll have some memory address that will denote by 0x and then some number. I literally just made up 329. That number itself, the value of it, not important, but this matching everywhere in our code will be important. You'll see in a second. But 0x to denote that this is a hex address, which is a memory location on your RAM stick. And then some value. So we're going to say this array is stored at memory address 329 in RAM, specifically in heap space for this program. So when our program starts, let me back up a little bit. We ask our operating system for a chunk of RAM and say, give me some stack space, give me some heap space, and then chunks of our RAM are allocated to the program. We get a certain set or certain range of memory addresses for our program. And we're going to throw this somewhere in memory and remember the address. This is where that thing is in memory. And then what's stored in our variable is only that address. OX, some number, box around it. So this number completely made up, but it has to be the same in both of these locations. Whenever we have that reference on the stack and whenever we denote that reference on the heap, has to be the same value. Because that, when you do that on the quiz, you're showing us, hey, I know that that argument, this variable named argument, is referring to this array on the heap. But wait, we make it even more clear. We draw a frickin' arrow too. Make it absolutely clear that that argument, this variable named argument, has a reference to this array on the heap. So that variable doesn't store the array. It stores a reference to the array. It stores instructions. This is where you can find that array in memory. It's at memory address 329. Go over to memory address 329. You'll find that array with its values. A lot to explain. We only got one line in. But that's a lot of what we want to talk about today. Next line, we have a method call. Method calls, and I did this in the previous example, but I'm going to assume all of you forgot about that. And I'm going to start over from scratch and re-explain things. If you do remember, I'm reinforcing it for you. When we have a method call, we're going to put what's called a stack frame on the stack. A stack frame is a completely separate environment that cannot interact with anything outside of that frame. So we have a stack frame, which we denote. I can do this. I got to cram it in up here. We have a stack frame, which we denote as a solid box on the stack. This stack frame is going to represent a method call. Internally on your machine, this stack frame will be added to the stack, and you can't cross this line. We're going to have all kinds of more variables and stuff going down here. Anything over here or anything in our method itself can't access these values. So in our code, in times 2, if in that method we say val x equals argument, we're going to get an error because we can't access argument. Even though it's in the memory of this program, since it's not in the stack frame of that method, we can't access it. These are completely isolated environments that don't share anything with each other. The only way we can get information from one stack frame to another is passing an argument to a parameter, which I conveniently named argument and parameter so we remember what those things are. So we get the parameter on the stack. All parameters go on the top of the stack frame. We name the stack frame with the method call or the method name. And we draw an arrow to the value that this method will return to. So when this method returns, the stack frame will be destroyed, and the return value will go into result. We denote that by an arrow, so we know the return value is going into result. And the parameter, what's passed, is the value of argument. Whenever we get a variable, we have to look up the value of a variable, and we're drawing these memory diagrams. Don't look at the code. Pretend that code don't even exist. Because you're going to be tempted to look through the code and try to figure out what argument is. Don't. You look at your memory diagram. What's the value of argument? It's OX329. OX329. So whatever the value is for that variable, then we draw our reference, go into that array. It's whatever is stored in that variable. Whatever the value is for that name, that's what argument resolves to, and that's what the argument is for this method. The parameter is equal to the argument. Look it up in your memory diagram. OX329, it's that reference. When you call a method that takes as a parameter something that's on the heap, it's only the reference that's passed. We're not making a copy of this array. We're not sending the entire array itself. We're only sending a reference to that array. Where can I find this in memory? It's like giving a roadmap. We're calling this method and saying, hey, here's a roadmap of where you can find an array. If you need this array, you need its values, go to that spot in memory and take a look at it. So there's only one array in this program, and it's being accessed through 2 different stack frames. All right, at this point, we're inside the method call, so I'm going to cover up main. The only thing main's going to do is print out result after this. So I'm going to cover this up just so I have some room to show you the rest of this thing. Where would the address that refers to the array be indicated at? Right here. So this is saying this array lives at 329, and then we have a reference on the stack in a variable with just that reference, just that 329. Hey, memory address 329, that's where you find this array. This 329, the value itself, that number 329, I strictly made up. If you go into your code, if you run the debugger, which I want to get a debugger example in here sooner rather than later in lecture. If you run your debugger, you actually see these memory addresses. You'll see them in the values of all of your objects. And they're pretty much just randomish, made up by IntelliJ, made up by the JVM as your program runs. We're not concerned about the values themselves, just what those values represent, which is where can I find this object? Will drawing the arrow be required on the quiz? Yeah, it will. Required is a strong word, though. Will capitalization matter on the quiz? I don't know. So I do want to talk about that. I want to answer both those questions in a little mini speech, though. The quizzes are graded by human beings. We're going to look at these things and decide 2 things. Is this submission good enough to show enough understanding to complete the learning objective? Did you complete the learning objective, which is like the bare minimum, like do you have a good understanding of the basic concepts that we were trying to convey, even if you might be showing a loose understanding of some of the more finer points? Do you understand what's going on with these memory diagrams? Can you draw out specifically stack stuff for learning objective 1? Do you understand what's going on the stack when a program runs? If yes, you get your learning objective. And then there's another threshold, another question we're asking. Do you really understand this in depth enough to earn that application objective? Did you knock it out of the park? Do you actually absolutely know everything about this? Did you internalize everything we were saying in lecture? Do you really get this? Which is roughly, if you're going to get program 3 on the quiz, will be the tough one. If you get that, that's where you're earning your AO. The first 2, that's where you're earning your LO, roughly. But these are graded by humans. We're going to use our big brain reasoning, big human brains, and figure out, as opposed to AutoLab, which has no brain. We're going to figure out, do you meet either one of those thresholds, either or both of those thresholds? So if you miss a capitalization, but you have everything else right, I'm giving you the AO. I don't care about a capitalization. Because what we're looking for is, do you understand how stack memory works? If you miss capitalization, that has nothing to do with your understanding of stack memory. If some of these arrows aren't there, if you're missing this arrow, but otherwise you have everything, you're still going to get that AO. So this isn't graded on, and that's a factor of derivative, I don't know. It's a feature of how we're grading these things, how there's the 2 thresholds. Whereas if this were percentage based and I was giving you a score out of 100 on these things, if you miss an arrow, I'm giving you at most a 99. But since we just had the 2 thresholds, we're not really sweating those little details as much as we would in another course. So if you miss a few little things, but you show the core understanding and another human being can see that you understand the core tenets of what we're trying to convey here, we're giving you that AO. We want you to get that AO. That said, if this arrow like points over here, well, now you don't understand what's going on. So that's tougher. If that were the only thing at all, it'd be a judgment call, and maybe you'll still get it. And you had everything else completely perfect on all three programs. But if like this arrow is just missing entirely, and these numbers still match, I'm feeling good about that. I feel like you understand what's going on at that point. So that said, mini speech over. Let's go through this program. We got the parameter. It was assigned the value of the argument, which I named argument here. We don't look at the code to see what that is, that it's an array 2, 5, 3, -3. No, we look at the stack. Argument stores this value. Whatever is in the value column, copy that over. Argument stores a reference, happens to be a reference to this array on the heap, but we don't care about that. We just care that that reference is copied over, whatever it refers to. Okay, sum, name value, name sum, value 0. And then we're going to hit a for loop. When we hit a code block, it's similar to a stack frame. Code block being anytime we see parentheses that don't define a method. Parentheses that define methods get stack frames. Parentheses that don't define methods, this is our if statements, this is our for loops. These are going to be code blocks. They share similar behavior to a stack frame, but not quite. They are a little different. So we're going to denote them by dotted boxes. And I'm leaving the bottoms of my boxes open because I don't know how much room I'll need. I recommend you do that on the quiz. I don't know how much room I'm going to need, and I don't want to draw the bottom lines and then not have enough room and really be cramming things in. I already got this little mess here that I messed up. I don't want to make more mistakes. The parameter spelled wrong, too. So I'm going to limit the amount of mistakes I can get into and not put the bottoms on yet. All right, so sum equals 0. We hit our loop. We get a new variable I, which is declared inside the loop. It's equal to parameter.indices. That's going to be 0, 1, 2. So we start out at 0. And we go inside the loop. We're going to create this value ram equals the return value of int times 2. So we have a method call, a new variable going on the stack, and we're going to have a new stack frame. So we have ram. I fixed this to be less confusing. I see there's going to be another issue coming up. Ram. Well, I'll talk about it when I get there, but geez. And we're going to have a stack frame for int times 2. We're going to draw int times 2, which I really have to cram in here. Int times 2, but the name of the method that's being called, and the return value is going to go into this variable ram. We have a parameter x equal to parameter of I. We're not looking at the code at all. We're going to look just at what we have in memory. This is the current state of memory when this method is being called. Parameter 329 is this array here. I is 0, so I want the value at index 0, which is 2. I'm just going to return x times 2. Ram gets 4. And whenever a stack frame ends, cross it out. That stack frame is no longer in memory. That x is no longer in memory. It doesn't exist anymore. It's gone. It's deleted from the stack. It's deleted from memory. X no longer exists. If we try to access x right now, we're going to get a variable not found. Next, we're going to say parameter of I equals ram. So parameter 329 of I0 equals RAM4. We're going to cross out the variable, the value, and replace it with its new value, 4. Then we're going to print. I forgot my section again. We'll have another section in out where we're going to write everything that's printed to the screen. And this, I expect you to do the same thing I just did on the quiz. Just put this, jam it anywhere you can. It's not going to be big enough to justify a 4th column here. Just put it wherever it fits, wherever you're not using room in another column is perfectly fine. We're going to print parameter of I, 4. Parameter of I was just 2, now it's 4, but we don't even have to think about it. We just follow the reference, get the value. Oh, it's 4 now. So we know what it is just by looking at our memory diagram, looking at the state of memory. Then sum plus equals parameter of I. This is where we see the difference between a code block and a stack frame. A code block, we can escape the code block. So when we hit sum plus equals parameter, sum is not in the code block that's currently executing, but we can still access it because it's in the same stack frame. So we can access variables in the same stack frame, but we can't access variables outside of stack frames. So that's why these are solid lines. We can't cross the solid lines. These dashed lines, we can cross the dashed lines if we need to cross that line to find a variable. So sum plus equals parameter of I, 4, sum 4. Oh, read the wrong thing. First value. So does the memory address point to the array object or the first value of the array? Kind of both. It will be the memory address of the first byte of the first value. But the way we think of it in this class, at least, is it's just referring to the entire array object itself. But a reference to an object is a reference to the first byte of that object. In other classes, and very briefly in this class, like I talked about random access memory, you have a value for the first, a memory address of the first value. If these are ints, so they're 32 bits, you would go up 4 bytes to get the next value, and then 8 bytes to get the next value to find the memory addresses of each subsequent value. That's a little bit outside of the scope of 116. It's more of a nice-to-know tidbit than, like it won't be on your interview or quiz. How complex will the programs be? Yes, similar to those in the examples. So on the example, the lab quiz this week, that's going to be roughly what your quiz is going to look like. Obviously different problems, but about that same complexity. Okay. So this returned I'm just going to make a little change right here. That actually does work with that being a val, but I don't feel like having that question and going down that rabbit hole. So we're just going to change that to a var. So we get to the next iteration of our loop. I is going to be the next value. It was 0. Now it's going to be 1. RAM is going to equal another call to int times 2. So we're going to create another stack frame. And I'm going to cram this in. When I'm doing this, it says int times 2. I'll write it here for completeness, even though it's going to look like just scribbles. But that says int times 2. We denote the name of the method being called next to each stack frame. And then this returns, if I can sneak my line right through here, excuse me, is going right into RAM. Yes.
On the quiz, could we like abbreviate a method and then clarify somewhere else on the page what that abbreviation means?
I suppose. I don't know. Yeah, if you need to, I guess. I would try to get it in there just to be. You know what I mean, to avoid like this problem where I'm making a mess.
Just where it's all. Correct.
Yeah, I wouldn't be mad at that. Yeah, instead of doing this crazy stuff I'm doing. We'll have shorter method names on the quiz too. They'll typically be called method 1, method 2. They won't have any meaningful names. And just since I said that, I should expand on that a little bit. They won't have meaningful names because we don't want to spoil like what they do. It's your job to figure out what the things do. So we don't want to give it some meaningful name and then you'll just reverse engineer the name. Just like you all do with the incorrect solutions on Autolab. You try to reverse engineer the names. That's not the intent, but I'm not talking about that one right now. All right, so we have a method call. X is equal to parameter of I. I've been talking for a while. I don't remember where we are in this program. I don't know what's going on. No problem. I have the entire state of memory right here. I actually don't remember. But we're going to have parameter of I. I is 1, so I know, now I remember. We're on the iteration of this loop where I is equal to 1. We're looking at the second value in this thing. That's 5. Memory diagram keeps me on track. This is why we do these things. It's easy to trace through the code and figure out what's going on. When I lose track, I don't have to go through the whole program from the start and figure out what the hell is going on. I just look at the state of memory. Got it. This 5 times 2 is going to be returned. RAM is equal to 10. Stack frame returns. It's destroyed. 5 is no longer in memory. Then we're going to say parameter of I equals RAM. Parameter of I equals RAM. So the variable I is not recreated. That's what I'm trying to avoid. So RAM could have actually been val because it does get recreated each time the loop runs. No matter how you represent that, I'm going to be okay with that. If you cross out RAM each time and re-add it to the stack, I'd be okay with that as well. That's more accurate to what's going on. Really, what I should have done is not declare a variable in my loop. Would have been the better thing for me to do here. But if you do it this way, or if you redraw RAM on the stack each time, either way I'm going to be okay with. Because the latter is more accurate, and the former is what I'm showing you in lecture. So I can't be mad at either of those. But yeah, that's why I could have actually got away with val here, because it's a new value. It's being destroyed when we hit the end of the loop, then recreated each time. I isn't being recreated. That's being... Actually, technically, is I being destroyed? Question for another day. So we get to print line parameter of I. Parameter of I. Looks like that's 10 now. And then sum plus equal parameter of I. Sum, parameter, I, 10, 14. Cross it out, rewrite the new value. Any other questions at this point? It is going to bug me now with the RAM. Maybe we should be rewriting it. How much does that bug me? I don't think it bugs me that much. Since there's no time where RAM isn't, on the stack at all. We'd just be crossing it out to rewrite the word RAM. Any questions? Would we have to rewrite the new code block for I as well then? Yeah, exactly. I don't want to go down that road because these things are going to get messy enough. You'll see very quick in LO2. I don't want to be doing too much like that because they'll get way messy. What does in out represent? That's everything that's printed to the screen. So whenever we hit print line here, we would print something to the screen. Okay, because otherwise we'd be crossing out the code block, writing a new code block, writing I, writing RAM, writing the stack frame, crossing all that out, writing new code block. It would get really messy if we went that path. Yeah.
Isn't it like, if you think about Java, for the for loop, it's for in I equals to something. So isn't it like technically you're declaring the whole variable in the for loop?
In Java, you're reusing the same variable because you do that variable, like you usually do variable plus plus at the end.
Yeah.
You are reusing the variable there. I'm not 100% sure if Scala redeclares I each time. I want to say it reuses that same I, but I'm not 100% on that. I think it reuses it the same way a regular for loop in Java would. I'm not 100%, but I know RAM is going to get redeclared every time. So we definitely have that question with RAM. But if you just cross them out, I'm going to be happy with that. I'm fine with that. You'll get full credit on your quiz. Because at that point, at the point that we're having that debate, I know you understand what's going on. Like you've definitely met the learning objective of the course. So if on your quiz you do one or the other and everything else is perfect, I'm feeling good about that. You understand what's going on in the computer. It's the memory. So we treat the memory address as referring to the whole array, but technically it's the first byte in the array. Because this is a single byte that it's referring to. All right, so let's move on. Int times 2. I promise this says int times 2. Times 2. X. Arrow, I'm going to try to keep this arrow inside the code block. Oh, my eye. And takes parameter of I. Oh, whoa, I'm getting ahead of myself. I, for this iteration of the loop, is going to be 2. And by the way, regardless of the answers to those questions, we're just going to cross out the values and go this way. If you do it the other way on the quiz, I'm still, I want you to get the AO because you're showing a deep understanding of what's happening. But if you're just crossing them out and ignoring that conversation we just had, perfectly fine. Parameter of I is 2. We get -3. Returns -6. -3 times 2. Cross out the stack frame. Parameter of I equals RAM. Parameter of I equals RAM. Print line parameter of I. -6 printed to the screen. Sum plus equals parameter of I. Sum plus equals parameter of I. -6. And then we hit the end of our loop. Nothing left to iterate over, so we can start closing this stuff up. We've reached the bottom of our code block, and we've reached the end of it. So cross it out. We cross out the last value of the looping variable. That's something, if you don't do that as well, nobody's going to get mad because I've seen Paul make that mistake. He may have made that mistake on the documentation telling you to do that. So that was definitely Paul's fault. Cross that out. Cross out the entire code block. So these variables no longer exist. I and RAM, gone. All these stack frames that were created for the 3 calls of that method, gone. All this stuff's gone. We reach the end of our method 2. We're going to return sum. Sum is 8. 8, a little messy here, but gets put into result way back on the main stack frame. result. We're going to close off our stack frame box. Cross this whole thing out. None of these values, parameters, sum, none of that exists anymore. It's all gone. All removed from the stack. Gone. We're all the way back on the main method now. Print line result. Result is 8. 8. And program ends. Now notice when we're back in the main method, in this method call, argument is still referring to the array at 329. That array, which used to be 2, 5, negative 3, so you would think right here in the code that argument is going to be 2, 5, negative 3 if you just look at the main method. But since times 2 had what we call side effects, meaning that it changed something in the heap, that array is no longer what it used to be. The argument is referring to this array, which is now 4, 10, negative 6. This is one big reason, it's an easy mistake to make. It's one big reason we don't look at the code to figure out what our values are. We look at our memory diagram. Argument reference to this array, 4, 10, negative 6. Not 2, 3, negative 3, or 2, 4, whatever it was. 2, 5, negative 3. It's not that anymore. So what was passed as an argument, when the argument is passed to this method, the parameter gets what's actually passed. And what the parameter gets is that reference. It's the reference to the memory address. Or it's whatever is in the value column. When we were calling this int times 2 method, we were passing an integer. We just wrote, okay, what's the value? What's the value that we have? Just put that in as your parameter. In this case, argument stored this thing. Just rewrite that whole thing inside your stack frame. It's whatever's in the value column. In this case, it's a reference. Only the reference is passed, not the entire array. No, not a copy of the array, not the array itself, a reference to the array, where to find that array in heap space. Any questions about that? No questions about that. What's the point of drawing the memory diagram? That is a good question. I don't think I motivated it well enough to pretend that you know what's going on. I like that answer. Can I just leave it at that? The point of drawing the memory diagram, so the big focus of this course is not just that your programs work, it's how they work, and it's how to write big programs. You can't write big programs if you don't even understand how your little programs are working. So we want to fully understand what's happening in memory when our programs run, so we understand what our programs are doing. And we see a lot of students who can make it through 115 and make it into 116, like halfway through the semester, doing perfectly fine, without really understanding what their code is doing. It does happen. It happens. The point of memory diagrams is to straighten that out. Understand what your code is doing. You'll be a much stronger programmer. You'll spend a lot less time on the homework assignments because you'll understand deeply what's happening in your programs, not just kind of getting an okay, fuzzy feel about how your code works. You'll understand for sure how that code works, exactly where the values are moving around, how things are stored in memory, and how these damn things work. What is this? This is computer science. Let's understand how these computers work. Not just how to hit the buttons in the right order to get them to do what we want, but what's actually happening in that damn thing. That's why we're doing memory diagrams, so we can have that deeper understanding and not just whack the keyboard until it works. Once you submit the lecture question, you can go. I got nothing else for you, and I'll see everyone Friday.